A teaspoon. That's the unit of measurement that breaks your brain first when you start studying neutron stars. 1 teaspoon of neutron star material weighs somewhere in the range of 10 million tons. Not the star itself, not a handful, a teaspoon, the kind you use to stir coffee. And that density, that almost incomprehensible compression of matter, is not the most dangerous thing about these objects. It's not even close. Neutron stars are born in violence. When a massive star, something between 8 and 20 times the mass of our Sun, exhausts its nuclear fuel, the core collapses. Not slowly, not gradually. In less than a second, a core roughly the size of Earth compresses down to a sphere about 20 kilometers across. The outer layers, suddenly unsupported, slam back inward at a quarter the speed of light, rebound off that newly formed core, and explode outward in one of the most energetic events the universe produces. What remains after that explosion is the neutron star, a city-sized remnant with more mass than the Sun, spinning, radiating, and existing at the absolute outer boundary of what matter is even allowed to do before it collapses further into a black hole. For decades, astronomers dreamed of what it would mean to study one up close. Not from afar, filtered through X-ray telescopes and radio dishes, but proximally. These objects hold the answers to some of the deepest questions in physics. What is matter like when it's compressed beyond the limits of ordinary atomic structure? What happens to the laws of physics at densities that no laboratory on Earth can replicate? The dream was to close the distance, to get real data from real proximity. It's a reasonable scientific impulse. When we want to understand something, we go to it. We landed on the moon, we sent probes to Jupiter, we skimmed the surface of the Sun. The assumption, born from that histo-ori, is that with enough engineering, proximity becomes possible. That assumption does not survive contact with the actual numbers. The surface gravity of a neutron star is approximately 200 billion times stronger than Earth's gravitational pull. Stand on the surface, which you cannot, but follow the reasoning, and you would weigh something in the range of 1 trillion kilograms. Every cell in your body would be compressed. Every organ would be flattened. The concept of standing becomes physically incoherent because the tidal differential across even the few feet of your own body would be strong enough to shred you at the molecular level. This is called spaghettification, and while it's most often discussed in the context of black holes, neutron stars produce tidal forces severe enough to begin this process at significant distances. The gravity doesn't just pull you toward the object, it pulls the side of you facing the star harder than the side facing away, and that difference, that gradient, tears matter apart. Your blood, your bones, your neurons, your atoms, they would be stretched into a thin stream of particles long before anything else had a chance to kill you. And as we're about to establish, there are many other things waiting in line. Even if tidal forces could somehow be neutralized, you would still face the radiation environment around a neutron star, which is so extreme it belongs in a different category of lethality than anything else we discuss when talking about space travel. Ordinary neutron stars emit intense X-ray and gamma-ray radiation continuously, but some neutron stars, the ones with magnetic fields trillions of times stronger than Earth's, are called magnetars. A magnetar's magnetic field is so powerful that at half the distance between the Earth and Moon, it would be strong enough to disrupt the iron in your hemoglobin. Your blood chemistry would fail. Every electron in every atom in your body would be affected. In 2004, a magnetar called SGR 1806-20, located roughly 50,000 light-years away, released a burst of energy in 0.2 of a second that was more powerful than everything our Sun will emit over the next 300,000 years. The burst was detectable from Earth. It partially ionized our upper atmosphere, from 50,000 light-years away. There is no material known to physics that shields against that. There is no hull thickness. There is no alloy, or composite, or experimental metamaterial that stands between a human body and a magnetar burst. The energy densities involved exceed the structural tolerances of matter itself. You would not be burned. You would not be irradiated in the conventional sense. The distinction between you and the surrounding space would cease to exist. But step back from the extreme case. Forget the magnetar. Consider a quieter neutron star, if such a description can apply to anything this violent. The background radiation field around even a relatively calm neutron star would deliver a lethal dose to a human being at distances still measured in hundreds of thousands of kilometers. The threshold for acute radiation syndrome, the point at which your DNA is being destroyed faster than cellular repair mechanisms can function, would be crossed almost instantly. Your white blood cells would collapse first, then your gastrointestinal lining, then the lining of your lungs. The immune system doesn't gradually weaken here, it experiences catastrophic failure. And unlike long-duration spaceflight, where radiation damage accumulates over months, proximity to a neutron star compresses that timeline into minutes or seconds. The cascade doesn't stop there. It never stops with a single cause when the environment itself is universally hostile. Even assuming some theoretical shielding addressed the radiation, the object's rotational dynamics introduce another layer of lethal complexity. Neutron stars spin. Some of them spin slowly, others, millisecond pulsars, complete over 700 full rotations every second. As they spin, they sweep beams of electromagnetic radiation across space like cosmic lighthouses, except the beam carries enough energy to sterilize a planet. The timing is not something you can dodge. The beam doesn't warn you. And because the star's gravity is warping space-time around it, predicting exactly where that beam will be requires calculations that account for general relativistic effects your navigation systems would need to solve in real time, at distances where communication delays back to Earth would be measured in years. Meanwhile, the star's surface is not static. Neutron stars experience starquakes, the equivalent of earthquakes, but triggered by the crust of the star, a lattice of exotic nuclear matter, cracking and shifting under the stress of its own magnetic field. A starquake can release more energy in 1/10 of a second than the sun emits in 10,000 years. There is no prediction window, there is no early warning system, there is no bracing for impact. The event would simply occur, and anything in the vicinity would cease to be. At every scale, at every distance, with every system we know how to build, the neutron star presents not a series of engineering challenges, but a series of physics violations, conditions where the rules that govern material survival no longer apply. This is not a problem of resources or willpower or technological maturity. The tidal forces are real, the radiation is real, the magnetic fields are real, the space-time curvature is real. No iteration of human engineering exists on a timeline that would produce a vessel capable of surviving even the outer radiation halo of one of these objects. That's not pessimism, that's an honest accounting of what the numbers say. And here is where the story turns, because the numbers also say something else entirely. We know all of this from Earth. From a small, warm planet orbiting an unremarkable star in the outer arm of a galaxy that contains hundreds of billions of others, we have never sent anything to a neutron star. We have never needed to. Mathematics and light have been sufficient to reveal the density, the spin rate, the magnetic field strength, the radiation output, the starquake mechanics, all of it, from incomprehensible distances. The fact that these objects would kill us instantly does not diminish our understanding of them. In some ways it deepens it, because to understand something you cannot touch, something that would unmake you at the quantum level, requires a quality of mind that is genuinely rare in the observable universe. We are fragile. Extraordinarily, almost comically fragile by cosmic standards. And yet here we are, mapping the crusts of objects we will never visit, calculating the interior equations of state for matter no laboratory can create, naming the beams of pulsars after the precision of atomic clocks. The cosmos has no obligation to be survivable, most of it isn't, but our curiosity has no obligation to stop at the boundary of what's survivable either. Some things in this universe exist purely to remind us of our scale. Neutron stars do that without apology.